Dear Gregory, can we start? Yes, of course. We
can do my
you're
best,
always
yeah.
ready. I know you're always ready.
Okay.
You're always ready for everything. So we did already, as far as we remember, we both remember, we did already the introduction. We did infinity and indeterminacy. We did the infinity of space. We did the infinity of time. And we can say that it was very complex, a very complex matter. But this time it's going to be even more complex because the new chapter is about finite complexity and infinite complexity. Would you say that in your career you encountered this concept, at first, this very concept of complexity, because now it's very fashionable to talk about complexity. And when did you, if you did actually, when did you encounter this concept? And did you actually, maybe not?
Well, I started very young playing around with these ideas. My version has to do with the size of computer programs. But these two questions, finite and infinite complexity, for me, they're sort of branded in my hide. Finite complexity, for me, what is it? It's the limitations of the formal axiomatic method. It's the failure, the very interesting failure of Hilbert's program to have a theory of everything for math. Any formal axiomatic theory that gives absolute certainty, which is what Hilbert wanted for all of math, has only finite complexity. And then infinite complexity for me is principally the omega number, which is a very concrete illustration of infinite complexity in pure math. But the omega number is there in the Platonic world of mathematical ideas. The world of mathematical ideas has infinite complexity, but we, poor humans, only have finite complexity, and our mathematical theories only have finite complexity. And there's this enormous gap. Now, the original reaction to Gödel's incompleteness theorem, which is a weaker way of saying that Hilbert's ambition to have a theory of everything for all of mathematics couldn't work, the initial reactions were despair by some people. Hermann Weyl, a great mathematician, perhaps the best student of Hilbert, actually, Hermann Weyl said he was so upset it pulled the rug out from under the reason he did math. He did math because math gave absolute certainty. It was this beautiful world, crystalline world of clear ideas. For 1 year, he couldn't do mathematics research, he said. Now, that's a loss for mathematics because Weyl was a very good mathematician. But my viewpoint is that it's good, not bad. If Hilbert had been right, the world of pure mathematics would be a cemetery where there would be no new fundamental principles. And if we recognize that it's finite complexity, but the world of mathematics is infinite complexity, what that means is we have infinite room for innovation, for finding new principles, for finding new concepts. It's an open system, not a closed system. It's not a cemetery. It's more like a garden that grows. And, you know, look at your daughter or our children, our grandchildren, God willing. There is lots for them to do. I think the idea that knowledge is unending, is the universe of mathematical ideas is infinitely complex. And that means that there's a lot to discover. It's endless. It's never going to be exhausted, not even the fundamental principles.
When I'm listening to you, it makes me come back to an idea that I already raised in our former chapters, that's supposed to become the chapters, is that it's like if mathematics, when it is, we could call it, let's say, low-level mathematics, when it doesn't deal with infinity at all. It's just like very close to what used to be called arithmetics and just calculations of things, etc. It's far. It's like if it was abstracted from reality, because it's like a model where you simplify reality, and you can say like even mathematics in his very low-level mathematics is just a formalization of the world. So formalization is what? It's just to simplify. You just simplify things. For instance, you have things that are like complex, we will say, like with different, it's hard to say if it is black or white. It's actually gray. And so you prefer to say it's black or white. And so it's binary. And so mathematics works like in a formal, very formal way, like a Cartesian way. You make things straight, where in fact they are never straight in reality. But when we think in a way at first sight with what I could call high mathematics, that you go far and far from reality, because it's not, it seems like it goes to, it reached this idea of infinity, and so you can't deal with it anymore. And so it become hard, it becomes harder to calculate with it, to understand even what could be a calculation with infinity, even if it is possible to make calculation, as you proved it in your work. In fact, it seems that we get far from reality when we do that, when we talk about infinity in mathematics. But it seems to me, on the contrary, that doing that, we actually came back. We make a turn, and we came back to reality as it is. Even more, we didn't come back to reality with the ty, but we come back to the real, to a real that is so direct that you can't actually apprehend it with formalization, with at least typical formalization. So you have to invent something that we still call formalization, but it is not a formalization like it will be a model of reality, like a simplification of reality. It's why we call it complex, and that's why we call it infinite complexity. But that's the real. That's actually the world we have around us. And that's also the reason why it feels like if we were far from perception. Why? Not because it is less real or less concrete, because in fact, perception is not to grab the concrete. Perception is an abstraction. It's right away the first level of formalization, because it's a model. All perception is a model. So mathematics, at a certain point, it's like if mathematics was freeing itself but from modelization of perception to something that is actually more real, and therefore doesn't look like something that you perceive, but just because it's more real, more what is actually life and reality.
Wow, I had to restrain myself from not interrupting you 20 times. This is such a rich topic.
Sorry.
No, on the contrary, very stimulating what you said. Let me start by saying, okay, one attitude is that mathematics is a simplification, which is certainly an important aspect of it. It's like a toy model of the real world, right? You don't care if it's 10 pheasants or 10 diamonds, you just have the number 10, right?
Exactly.
And that's certainly true. And von Neumann said pure math is simpler, it's easier than real life, right? But there's another attitude which says that look at a table. This is a remark by G.H. Hardy in his book, A Mathematician's Apology. You look at a chair, the closer you look at it, the more it dissolves, the more strange it seems, because you have to use Schrodinger's equation, quantum mechanics, why is it stable, why doesn't it collapse? The more you look at it, the more mysterious it becomes. But he said, 2 + 3 = 5 is real. There you are in direct contact with reality. So the other attitude is not that the numbers are a simplification, an idealization, an abstraction so that we can cope with the complexity of the world. The other attitude is to say 2 + 3 = 5 is more real than a table or a chair or than this mess of reality, because there we touch reality. That's one of the few places where human beings can actually touch mathematical reality. And this may be the reality out of which God, to use a metaphor, created the world, because you have to build the world out of something. And I keep giving the example of marshmallows from my Boy Scout background in the United States, roasting marshmallows in the fire. You can't build the world out of marshmallows. You need some kind of brick, something very solid and clear to build the world out of. What could it be? Well, one possibility is to build it out of mathematics. Another possibility is to build it out of information. Now, another issue you raised is discreteness versus continuity.
Exactly. Exactly.
The infinite sometimes is simpler than the finite. There are areas of mathematics where if you go to the limit of continuous limit instead of looking at a problem as a discrete mesh, for example, the math actually gets easier. It gets easier. We mathematicians sometimes feel that the real world is unreal. The only real world for us is the world that we deal with in our math, because there things are sharp, things are clear, things are either true or false. And in the real world, everything is a mess in the so-called real world. So where is it? What is reality? I don't know, but 2 + 3 = 5 seems to be clearer and more real, at least to a mathematician,